Hello, my name is Yuze from Virginia Tech. Today, I'm going to talk about our work in memory tiering in Python virtual machine. So this is a joint work with collaborators from Virginia Tech and Rochester Institute of Technology. And this work is also partly funded by NSF. So Python is the world's most popular programming language. It's simple and has powerful libraries. But this simplicity comes with a hidden cost. It uses a lot of memory. Python virtual machine maintains metadata such as object type and reference counting information. A simple integer in Python can take up to 28 bytes, while only 4 bytes in native languages like C or C++. This Python programming more quickly. So a typical way to solve this problem is through memory tiering. The idea is very simple. You equip a server with two types of memory. First, you have a small but very fast tier, which is usually your local DRAM. Think of this as your desk, limited within arm's reach. Then you have a much larger, cheaper, but slower tier, enabled by new technologies like CXL. This is like your cabinet, which has massive storage, but it takes a moment to retrieve things. So the goal here is to keep your frequently used or hot data on your desk and less used or cold data in the cabinet. Essentially, what we are trying to do here is to achieve a better trade-off between application performance. The goal here, of course, is to know exactly what's hot and what's cold at any given moment. So how is this problem typically solved today? There are two main approaches, but unfortunately, neither is a good fit for Python. The first approach is managed by the OS. The OS watches which memory pages are being accessed and moves them between tiers. But this has two major flaws. The first problem is one policy fits all. The OS treats all user-level applications equally and applies one tiering rule to all applications. However, this does not work well in today's cloud because different applications have different quality of service requirements. For example, some workloads are latency sensitive, while some others are memory heavy but can be purely background tasks. So it's impossible for the OS to make specific tiering configurations for these different types of applications. The second problem is when the OS tracks page hotness, it needs to sample page access bits or relies on hardware counters. Hence, it comes with a hidden trade-off between the sampling accuracy and the overhead. It's either introducing significant overhead that slows down the application or could be inaccurate, leading to poor decisions. So as you can see in this set of figure, if you increase the sampling interval or decrease the sampling granularity, although the tracing accuracy would drop, although the tracing overhead would drop, the accuracy is significantly hurt. As you can see, the boundary between the hot and cold addresses are barely distinguishable. The second tiering approach is to build tiering directly into program language runtime. These solutions are much more fine-grained that can track individual object hotness. Plus, users can make application-specific tiering configurations. This is a great idea, but the solutions that exist today are built for other languages. In JVM-based runtime, you can instrument the read and write barriers to mark an object being accessed. Python doesn't have these barriers. In C++, you can overload the smart pointers and the dereferencing operator to track every time an object is used. Like you see in this figure, the smart pointer uses the first 2 bytes as a hotness tracker. When the is dereferenced, will increment. However, the underlying implementation of Python is in C that doesn't support this feature. Essentially, the fundamental problem is Python doesn't have the program language feature to enable tracking object hotness, making it very hard to build a memory tiering system. So how did we solve this? We found a new way to infer Python object hotness by using a feature that is crucial to Python memory management, reference counting. Python uses ref count for garbage collection. It increases when a new name points to the memory object. When all references to the object are removed, the object is logically freed. Let's look at an example of how Python evaluates a simple statement, C equals to A plus B. It does this by maintaining an operand stack. During the evaluation, the object's ref count are changed. Initially, we have variables A, B, C, whose ref counts are all 1. First, A is pushed into the stack. Its ref count increments to 2. Same thing happens to B, whose ref count also increments to 2. Then A and B are popped from the stack, followed by a binary add operation to add both A and B. Note that A and B's ref count drops to 1 after popping. The evaluation result is then stored to C. When pushing into the stack, its ref count pops to 2. Finally, after the statement evaluation is finished, C's ref count drops to 1. So notice that although the ref count variables in evaluation, they did get changed during the process. So our observation is, although ref count does not directly indicate object accesses, we can observe its changing behavior to infer their hotness. Our system therefore uses this observation to track Python object hotness. We do this by reusing the existing OB ref count field. The 32 least significant bits are left for the original reference counting purpose. We make use of the 32 most significant bits to keep track of the ref count changes. However, unlike the original ref count, our MTP count only increases no matter the original ref count increases or decreases. With that, I'll present MTP. This is a C extension module built on top of C Python interpreter. Once enabled, it runs as a background C Python thread. It first performs a marking phase to obtain all Python live objects. Then it enters several consecutive sampling phases to obtain Python object reference count changes. During the sampling, we periodically predict the sampled object hotness using our inference model. After the object hotness are obtained, we enter the migration plan for data promotion and demotion. Here we use a eagerness-driven metric to calculate hot versus cold page threshold. Because the marking phase temporarily needs to block the application, we have if that is not. I will now describe each component in detail. So to start with, MTP needs to have the full scope of all interested PyObjects. The internal Python virtual machine does maintain 3 generational GC lists to detect cyclic references, where we call cyclic GC lists. Unfortunately, these lists only track container objects, for example, list, tuple, or dict. If we only sample their hotness, a large number of objects will be skipped. So we perform a marking phase to obtain all Python objects. It works by recursively traverse all Py objects starting from the cyclic GC list like this. Once facing an iterable object, it further traces to its children object. The marking finishes until all marked objects have no children left. However, this marking phase must be stopped the world, which temporarily blocks the application. So we have to mitigate the overhead as much as possible, but still maintain an acceptable tracing accuracy. So how do we do this? We found two mitigation solutions. The first one is that we're trying to minimize the number of calls to the marking. We find out that this can be inferred by observing how CPython cyclic GC behaves. We observe that when only few cyclic GC gets triggered, the number of new objects is also very low. That means it is meaningless to initiate a new marking phase. Based on that, we'll temporarily skip current marking phase when cyclic GC activity is not intensive. While this may slightly reduce marking accuracy, missed object will be detected in subsequent markings. On the contrary, if we observe a lot of cyclic GC happen between two consecutive markings, only then would we enforce a complete marking phase. The second mitigation solution is to make sure that within one marking phase, the time taken would not be unbounded. So we transcend the nested levels of the current container Py object being traversed, and it will stop marking immediately when either of them meets the predefined threshold. As you can see in this figure, we set these two different thresholds, values with different thresholds that can control the trade-off between the marking accuracy and the overhead. The more aggressive MTP confines the threshold, the less blocking time it would take. Once MTP obtains the scope of all Py objects, it enters several consecutive sampling phases. Here, we're trying to capture their ref change and the user hotness. So how do we train the model in offline? We collected Rafique changing behavior from several workloads. Then we calculate their statistic like median, standard deviation, number of non-zero changes, and use ground truth with offline using demo, which samples OS page hotness. And we then align the Python object addresses to those page boundaries, representing the hotness of those pages, of those objects. We choose several model architectures and fit the model with the above matrix. Note that all of these are done offline, only once. Here we show the performance of our hotness prediction model. All models actually predict the object hotness pretty well. For instance, multilinear regression, or MLR, shows a 0.7 R-squared and achieves a Pearson correlation of 0.84, indicating a strong positive relationship with the actual hotness. So here we show a visualization of a hotness heat map of a matrix multiplication workload from the OS page sampling. On the right-hand side, this is the visualized heat map when we are using our prediction model, solely using the Rafique changes. As you can see, they look very similar to each other. This indicates that MTP can accurately predict object hotness within Python virtual machine without sampling OS page information. MTP triggers the migration plan to move objects between tiers. To do that, it aggregates all objects' hotness inside that page. For example, a page with 3 objects, hotness 3, 4, and 3, has a total hotness of 10. We maintain the page hotness information using a hotness histogram. All pages within a bucket in that histogram has the hotness ranges belonging to a range. This is the standard practice for OS-based tiering solution. Once our hotness histogram is populated, MTP needs to decide the bucket threshold between hot versus cold. Determining this threshold is relatively easy for OS-based tiering solution. Why? Normally, the total size of the pages in bucket H and above is just below the fast memory capacity. This is because OS tiering solution can see all system physical pages. However, integrating the exact scheme into MTP is infeasible, because here MTP doesn't have the global view of all system pages. So using the fast tier capacity to set this threshold doesn't make sense. To accurately determine the hot versus cold page threshold within the Python program, we introduce a new matrix called eagerness. Here, I represents a time interval. We consider three factors to calculate the eagerness: the percentage of pages currently located in fast tier, eagerness of the last level cache misses, and the eagerness of the bandwidth going to the slow tier. The eagerness of LC miss is basically the z-score of pages encountering the LC miss. A higher eagerness value indicates more fluctuations that current system deviates from the previous cycles. Eagerness bandwidth is calculated similarly. MTP uses this information to iterate through the histogram buckets, starting from index 0 and moving to the right, one step at a time, until it finds a bucket index H where the number of pages in the fast tier is the number of hotter pages in the slow tier. This initial H is considered as the most eager threshold. If we see a decreasing of the eagerness value, this means that the current hot pages are less eager for promotion compared to the previous cycles. In this case, the threshold H is moved to the left by one bucket. We also provide a simple interface for cloud providers to use our system. Once imported, mtp.start will start monitoring the current fast tier memory size. When it falls below the memory pressure, the marking phase will then start. The mask here is the memory node mask for demoting code data. The sample interval controls the interval for sampling phases. Finally, mtp.end will stop the MTP thread and freeze all metadata. As you can see, this simple API enables per Python program, even importantly, per code segment tiering control. To use it, cloud providers can integrate this MTP into the Python instances, for example, in their serverless platform, to control the tiering behavior for different workloads easily. For example, for latency-sensitive workloads, like web applications, you may want to set a high memory pressure and medium sample interval to reduce the MTP marking overhead and reduce remote access latency. For long-running background tasks, like batch processing, you may want to use low memory pressure and high sample interval to maintain acceptable performance without impacting the high priority tasks. We now show the evaluation. So we use a machine equipped with two CPU sockets, CPU 0 and CPU 1, to simulate a CXL-powered tiering system. We disable all the cores on the CPU 1 so that only CPU 0 As you can see, compared to the state-of-the-art tiering solutions, TPP MEMTIS, MTP outperforms them significantly. For example, in A*, which is a pathfinder graph algorithm, under which is 25%, MTP outperforms TPP for about 1.24x. This is due to OS inability to track fine-grained memory access and falsely demotes hot pages to the slow tier, causing the performance degradation by TPP. Across 33 comparisons, MTP outperforms TPP in 25 cases, AutoNuma in 30 cases, and MEMTIS in 15 cases. I have to admit that for some workloads, MTP doesn't always perform the best. We identified two root causes. First, MTP spends a huge amount of time during the very first marking phase, because at this time, we have no prior knowledge of the Python object scopes. Thus, it needs to perform the most exhaustive marking across all the objects. The marking time scales with the object scope. Sometimes it might overshadow the migration benefit. The second overhead is that MTP interposes the object reference count changing manipulation paths. Remember, we increase the value of MTP count whenever an object ref count is increased or decreased. This step is in the critical path that adds additional CPU overhead. To summarize our work, in this project, we propose MTP, a C-Python integrated memory tiering system for Python applications. MTP infers fine-grained Python object hotness from reference counting changes without relying on OS page sampling. It utilizes existing cyclic GC module in Python VM to mark objects and reduce unnecessary overhead. To determine the hot versus cold threshold for application itself, it utilizes a eagerness by considerer wants to be promoted to the fast tier. It can deliver performance that is comparable or superior than state-of-the-art OS-based methods. But most importantly, we provide customizable per application tiering opportunities. This allows the cloud providers to tailor memory management to specific QoS needs of their Python applications. This will unlock significant efficiency and performance gains in modern data centers. Thank you, and I would like to take any questions.
For this presentation, what?
Sorry, you were muted for the first 5 words.
Okay. Hello. Now you hear me, Yuze. Thank you for the great presentation. Do we have any question for Yuze?
Okay, so I'm going to. Hello, can you hear me?
Yes, you are unmuted.
Sorry?
Your mic is live. You just have it on.
Okay, so, right. Thanks for your talk. I'm wondering, how do you envision integrating MTP with existing Python runtimes such as PyPy or other just-in-time compile-enabled interpreters?
Okay. So your question is how to integrate MTP into native executables like NumPy or TensorFlow, right?
Other interpreters like PyPy or, so I'm also interested.
Okay. Got it. Thanks for your question. That's a good one. Actually, our system currently only is built on top of CPython 3.10. And for PyPy or like other Python build, they probably are implemented by different, for example, different GC or different memory management module, which requires a complete different tiering solution than CPython. So we just choose the CPython because this is the world's most popular deployed distribution. But yeah, we should look for other distributions.
Okay, thanks so much. So I'm also wondering how is the applicability to NumPy or other kind of stuff?
Okay, that's a good thing because as you can see, the whole scope of the MTP is only applicable to Python objects, like the object who has a PyObject header, right? So if you want to enforce MTP for other like native executions inside the Python programs, current system you cannot do that because those objects are not Py objects, so we cannot track their reference count changes, right? So one solution I can think of is to temporarily lock MTP threads, but we can use of other OS solutions while running the native executions.
Yuze, I have some questions on my side. The first one is that, okay, it's good to see the memory tiering in Python runtime. It's not very obvious to me what is the problem. I mean, and I'm going to explain you. The problem is that you say at the start that the headers of the Python objects takes much memory. Okay, this is not something new because also Java objects takes much memory because they contains a header. The problem that we want to have memory tiering in Python is that we demand more memory for applications, and if yes, what is this application that they demand a lot of memory? And also large address spaces, for example. And also, how much is the cost of the garbage collector in Python in this kind of setups? Yes, if you can tell us. Yeah.
Okay. So your concern is regarding the not with the object header, right? But the application memory. Okay.
Yeah.
So regarding that, I think we tested a lot of more than 20 actually workloads, and okay. So the thing is, I agree with you that the JVM and the CPython also both have their own object headers, right? But unfortunately, the PyWorks only handle. I'm talking about within a program language runtime. They only target C++ or JVM. But Python this is an untouched area. So we purely based on that one of the premises, we built this system, which only works for Python. So similar, semantics works also for JVM that they couldn't work for Python. So this is not about the header problem, but more of the the program feature enabled tiering solution. So regarding your second question about the GC overhead, right? I think as I mentioned in the previous slides, let me go back to that. Okay, so our overhead comes from the two parts, right? One is the marking overhead, which is purely original system, because the CPython itself doesn't maintain the full object scope. So that we have to pay for the price for the marking, at least for the first time. And for the second part of the overhead, it comes from the CPU additional overhead in the critical path, when it's trying to increment or decrement the reference counting, because we're trying to have a MTP count separate from the original reference counting. So we note that at this project, we do not make any changes to the existing CPython GC. CPython GC has two parts, right? First part is the reference counting. When the reference count drops to 0, it is logically freed. Second part is the detect of the cyclic references. We're not changing any of this existing GC logic. So, well, yeah, does that answer your question?
No. So in a breakdown of your time, the GC, it might be the same in all in TPP, Autonuma, Memtis, MTP. But what is changed is let's say, the application thread time. Is it this part?
No. So you're talking about these slides, right? So on we show the perform better. Isn't that MTP does not perform the best in terms of runtime is because of those overheads that I just explained. And for the baselines, the TPP, Autonuma, Memtis, they are all the OS-based their own overhead, but their overhead does not stem from the Python virtual machine, but stems from the OS page sampling.
Okay.
Yeah, so they're coming from different sources. Yeah.
Okay. Thank you again for the presentation. I don't know if there is any other question. No? So
Thank you.
We can continue with the third presentation for today. So the floor is yours.
Okay, thank